At the Max Planck Instituut in Frankfurt, the theory of general relativity is used to study observations of black holes and neutron stars. Luciano Rezzolla is one of the leading scientists. Running Einstein's equations on the computer provides him with realistic simulations.
Up and then would go down like this. So it is very clear when the ring down starts, which I think if you look at it in terms of waveform, it's confusing because you don't know, do I start here or should I start here? So this is the rendering of a simulation. Here we are solving the Einstein's equations on the computer. So this is no computer graphic, this is real mathematics. You can look at mathematics as a series of numbers, or you can look at mathematics in this way. It's the same. Still numbers behind this. You can't get a stronger gravity than near a black hole. Being a black hole alone doesn't make gravitational waves. You need motion, you need dynamics. And in order to have dynamics, you want to have a binary system of black holes. That is, two black holes that move around each other. They are attracting each other, and at the same time, they are trying to avoid each other. So they go around each other in this, what we call in spiral. They are losing energy. They are emitting these gravitational waves. These ripples that are produced by the motion of these two objects. This little sheet here is space-time. It's a slice of space-time. Inside there are two black holes. So we need to dive into this space-time in order to see the two black holes. And they are over there. They are those two little balls. The curvature is almost flat everywhere, but close to the black holes it is not. See how severe the curvature is. And in fact, it goes like into a needle. If you let these guys follow the Einstein's equation, what they will do is they will rotate. And as they rotate, they produce gravitational waves, which are shown with this, psychedelic color here. You have yellow, which is positive, and red, which is negative. Because they are getting closer and closer and closer, at one point they will get so close that they merge. And this is the very time when they merge, and they produce a single black hole. So this is the horizon of the merged black hole. And now I zoom out so you can see the gravitational wave field. So this is what has been produced for millions of years. It's just that only at the very end, the signal is so strong that it can be detected. So that's the merged black hole. And as you can see, there is no signal now. That's because when a black hole is formed and is axisymmetric, it's a single black hole. And we said a single black hole alone doesn't produce any gravitational wave. This part here is the part that goes up and down. Then you can see here the separation between the crest becomes smaller. And that's when the wave becomes very, very, narrowly separated. And then here there is this hole. That's when the signal stops. Okay, so this is the ring down. So if you see that ring down, then you know that there is a black hole. And a black hole is defined by the fact that there is no surface. There is just an horizon. It's a bit like a fingerprint. Okay, the two black holes of different times will produce a very specific signal. And that's what we do. We spend a lot of time computing these waveforms. May I show you something else? Here you have the two stars, which are these two little eggs, but these are the two stars. And here I'm showing you the gravitational wave as it will be measured by a detector from this. So at the beginning there is nothing, but then you start seeing the signal, and you see that the signal goes up and down just like you were expecting. Now the two stars have merged. The system is so heavy that it has produced a black hole. It's the one you see, the little green P. And this is the gravitational waveform. And this part here that you see that stops, that's the ring down. In a binary system of neutron star, this is what you can produce. You produce a black hole and then some matter around it that has not fallen yet onto the black hole. What is it that makes a difference between a black hole and a neutron star? Mathematically, they are very different. A black hole is a solution of the Einstein's equation in vacuum. There is no matter. You can't find a single atom in a black hole. because the idea is that everything is at the center and everything is in a dot. So they are vacuum solutions, while a star is a star. It's a very dense object, but with a surface, something you can throw an hammer at. Something they have in common, though, is that they don't just deform the space-time, they can also set it in rotation. If you are a little object in a tornado, you cannot stand still. You will have to turn together with a tornado. And here is not a tornado, but it's the whole space-time that is rotating because of the presence of the black hole. So far we've just given prediction, but we haven't had any way to tune our theories, to understand whether what we're doing is right or wrong, whether certain assumptions are right or wrong. For us, having a detection is also very important, because we limit our freedom of exploring parameters. We know certain things simply cannot happen.